All right, good morning. Welcome to my stream. Let's see. So yesterday we finished, there we go. We finished up the while loops, and we also did these are while statements, right? We did if statements. If statements gave us a jump forward, two jump forward instructions, jump if false and up jump. And while loop gave us the loop statement, the loop opcode, which is a jump backwards. And then we spent a little time trying to fix up the JLOX version of the code to try to get it to compile, or to pass all the tests rather. And there's this issue here I need to solve. I think this is the biggest issue, is the illegal expression stuff. Yeah, you see that all over the place. So we need to fix that. But we're going to start off looking at this section here, which I got to figure out where the top of is. There we go. 4 statements. All right, so we should be clean. And we are. And we should, if I cargo run, I do have while loops. I have if statements. If 1 equals 2, print yes, else print no. And we print no. So the if statements are working, and then we can say var a equals 5 while a is greater than 0, print a, and then a minus equals a minus 1. We don't have minus equals. A equals a minus 1. So we print, it's kind of long, but it all's there. There's 5 right there. 4, 3, 2, and 1, and then it stops. So those are the whiles and the ifs. So now we're going to do fors, and fors are a little more complex because they're going to be done in, if it's similar to the way we did it in JLOX, they're going to be done in as a while loop that's kind of funky. So one sec. Okay. All right, so for statements. The other looping statement in LOX is the venerable for loop, inherited from C. It's got a lot more going on with it compared to a while loop. It has 3 clauses, all of which are optional. The initializer can be a variable, declaration, or an expression. It runs once at the beginning of the statement. If you want to refresh, the corresponding chapter in part 2 goes through the semantics in more detail. Yeah. The condition clause is an expression. Like in a while loop, we exit the loop when it evaluates to something falsy, and then the increment expression runs once at the end of each loop iteration. In JLOX, the parser desugared the for loop to a synthesized AST for a while loop, with some extra stuff before it and at the end of the body. We'll do something similar, though we won't go through anything like an AST. Instead, our bytecode compiler will use the jump and loop instructions we already have. Okay, we'll work our way through the implementation a piece at a time, starting with the for keyword. All right, so dive right in here. This is in statement. So it's at the print statement. There's an if statement. So it's just before this. If self is match. Token type 4, and we're going to do self for statement. Simple enough. It calls a helper function. If we only supported for loops with empty clauses like for, semi, then we could implement it like this. All right, so we're just putting the skeleton of it in here right now. Oh, expression statement. There we are. I'm just reading this here to see where to put it. In C, it matters where it goes because you have to declare it before you use it. But in Rust, it doesn't matter where it goes. But I'm still following their suggestions here. It saves me having to think about where to put it. Consume left paren, consume semicolon. Expect after 4, like that, and then we'll consume a semicolon, expect semicolon. Okay, I'll put the other two consumes in here now, because there is another semicolon, and then we have a right paren. So expect right paren after 4 clauses, like that. In between, though, we have loop start. Let loop start equals self chunk count, and then self statement and self emit loop start. Okay, and then of course we're going to need the expressions in there. There's a bunch of mandatory punctuation at the top. Then we compile the body like we did for while loops. We record the byte offset at the top of the body and emit a loop to jump back to that point after it. We've got a working implementation of infinite loops now. Alas, without return statements, there isn't any way to terminate it short of a runtime error. So now we're going to get to the initializer clause. We'll add the first clause, the initializer. It executes only once before the body, so compiling it is straightforward. So this is going to be... Oh, I'm just looking here to see where the semicolon goes. And I guess we don't care about that anymore? That's... That's confusing. Where does... Oh, instead of doing it, we're going to do the match. I see, okay. Sorry, that took me a little while there. So we'll say instead, if self is match, token type semicolon, no initializer, else if self is match, token type var. So if we have a variable declaration, self var declaration. Otherwise, we're going to assume that there's an expression statement there. And then we do the loop start stuff. Okay, this syntax is a little complex since we allow either a variable declaration or an expression. We use the presence of the var keyword to tell which we have. The expression case we call expression statement instead of expression. That looks for the semicolon, which we need here too, and also emits an op-pop instruction. Consumes semicolon. There. I'll just put that for my benefit if I ever look at that again. Emits the op-pop instruction to discard the value. We don't want the initializer to leave anything on the stack. If a for statement declares a variable, that variable should be scoped to the loop body. We ensure that by wrapping the whole statement in a scope. So that's interesting. The scope is going to be generated even if we don't need one. Right? If there's no variable declaration here, we still needed to have generated the scope. And then after the emit loop, we'll do the end scope. Okay? Then the condition clause. Next is the condition expression that can be used to exit the loop. Okay. So after loop start, this is where we set exit jump. How would we do this in Rust? This is a sentinel value, right? Yep, it is. So we're going to check to see if it has a value. So we're going to use the standard Rust option thing here, and we're going to say right here, we're going to say let exit jump equals if match is, I'm going to flip this condition around, self is match, token type, semicolon, right? Basically taking this thing here. Right? If it's match semicolon, then it's none. Else, we're going to do this work here. We're going to say self expression. Oops, I took away that. Let's copy that guy. expect after loop condition. There we go. And then jump out of the loop if the condition is false. And then we're going to say let, I don't want to use the exit jump again, result will self emit jump op code jump if false. Self emit byte op code pop into, and then we're going to have this result be the result of the if expression. Right, so this is basically setting it to -1 if it doesn't match. Sorry, if it does match the semicolon, we want to set it to -1. In our case here, we want to set it to none. And then this needs to be some result. I think it's probably cleaner to do it this way, because that way you can see the none versus the sum here, rather than the sum being hidden somewhere in there. Then we can just separate that, and we go like that. So now exit jump is either going to be the result of the emit jump, or it's going to be a none. Since the clause is optional, we need to see if it's actually present. If the clause is omitted, the next token must be a semicolon. So we look for that to tell. If there isn't a semicolon, there must be a condition expression. In that case, we compile it. Then, just like with while, we emit a conditional jump that exits the loop if the condition is falsy. Since the jump leaves the value on the stack, we pop it before executing the body. That ensures we discard the value when the condition is true. After the loop body, we need to patch that jump. Okay, so we emit loop, loop start, and then we say if let some exit equals exit jump self patch jump exit self emit byte op code pop into. Okay, we do this only when there's a condition clause. If there isn't, there is no jump to patch and no condition value on the stack to pop. Okay, I think that works best. Increment clause. I've saved the best for last, the increment clause. It's pretty convoluted. It appears textually before the body, but executes after it. If we parse to an AST and generated code in a separate pass, we could simply traverse into and compile the for-statement AST's body field before its increment clause. Oh, I see. Yeah, so if we did it like a two-pass kind of thing, where you convert it to an AST and then use the AST to generate bytecode. Unfortunately, we can't compile the increment clause later, since our compiler only makes a single pass over the code. Instead, we'll jump over the increment, run the body, jump back up to the increment, run it, and then go to the next iteration. I know, a little weird, but hey, it beats manually managing ASTs in memory in C, right? Here's the code. Okay, so this is saying if we don't have a right paren, so this is right here after the close. After the close paren. Oh, we're replacing this line. Well, sort of. Self. If not self is match. Token type. Right paren. If we don't see a right paren, then we have the increment clause. And we're going to say let body jump equals self emit jump opcode jump into let increment start is equal to self chunk count. We're going to do this expression. We're going to emit the pop byte to pop off the expression, I guess. Opcode pop. And then we're going to consume the right paren. Right? I'll leave that alone. We'll emit the loop, self emit loop, loop start, Then loop start gets reassigned. Okay. Loop start equals increment start, and then self patch jump body jump. And then we're going to have to modify loop start to be mutable. Okay. Again, it's optional. Since this is the last clause, when emitted, the next token will be the closing parenthesis. When an increment is present, we need to compile it now, but it shouldn't execute yet. So first we emit an unconditional jump, that's this guy here, that hops over the increments clause's code to the body of the loop, right to there. Next, we compile the increment expression itself. This is usually an assignment. Whatever it is, we only execute it for its side effect, so we also emit a pop to discard its value. The last part is a little tricky. First, we emit a loop instruction. This is the main loop that takes us back to the top of the for loop, right before the condition expression, if there is one. That loop happens right after the increment, since the increment executes at the end of each loop iteration. Then we change loop start to point to the offset where the increment expression begins. Later, when we emit the loop instruction after the body statement, this will cause it to jump up to the increment expression instead of the top of the loop like it does when there is no increment. This is how we weave the increment in to run after the body. It's convoluted, but it all works out. Complete loop with all the clauses compiles to flow like this. All right, so we have the initializer clause, right? I mean, if we let's just use a for loop, for example. Oh, we don't have one. So let's just do this for int a. I'm writing it in C. Equals 1. A is less than 10. A plus plus. All right. So we have the initializer clause, which runs. We have the condition expression, which gets checked next. If it's false, we jump out of the loop, right? If A is not less than 10, then we're done with the for loop completely. We then run the body, right? We op jump to the body statement, run the body, and then we call op loop to go back to the increment expression. So it goes here. This pops, and this loops back up to the condition expression. This pops after the increment is done, right? So we do A++, which is going to have the side effect of leaving A on the stack. We pop A++, or we pop the result off the stack and then loop back to the condition. So we run this, and we jump back to here. We run this. If this is still true, then we continue with the body, with this op jump, run the body. Otherwise, we jump out if it's false. So it is a little convoluted because you do this first, you do the condition, you run the body, you do the increment, and then you do the condition. One other option would be to put the increment expression after the body statement. So the body statement would just fall through to the increment. But then we're not able to, since it's a single pass compiler, we have to do it in this order. And we have to generate it in this order because this is the way we're reading it from the token stream. All right, let's see if this even builds. Wow, okay. No errors, no warnings. As with compiling for loops and JLOCs, we didn't need to touch the runtime. It all gets compiled down to primitive control flow operations the VM already supports. In this chapter, we've taken a big leap forward. CLOCs is now Turing complete. We've also covered quite a bit of new syntax, 3 statements, and 2 expression forms. Even so, it only took 3 new simple instructions. That's pretty good effort to reward ratio for the architecture RVM. Oh, is this the pun taking a big leap forward? Okay. I didn't even see it. Let's see if for loops work. Cargo run. For A equals 0, A is less than 5, A equals A plus 1. Oh, I have to say var A. A equals A plus 1. print A. Seems like it worked. So we have this, the constant 0. Get local, statement 2 is get local 0. We have a constant of 5. Oh, get local 0. 0 is the A, right? That's the local on the stack. We check to see if it's less. If it's less than 5, then we ignore that instruction. If it's 5 or more, then we jump to 31, which does a pop. Ooh, 2 pops. If the expression is true, we pop the result of that expression off the stack and then unconditionally jump to 25. 25 gets A again, prints it, and then loops back to 14. 14 gets A again, pushes 1 on the stack, and then adds 1, and then sets A to the result, and then pops something. And then it loops back to 2, which gets A, and then checks to see if it's 5. Okay. So I think that all works. It's very convoluted, right? I mean, if I were to write this in assembly, I wouldn't do it this way. But this is what we get when we do a single pass compiler, and we have to generate all the instructions in the order that we see them in the text of the source. All right, and it's working. I think I can say no default features. Let's try it this way. Yeah, and then we have, ooh, maybe this is something I should also add to. Yeah, when we run no default features, we shouldn't have all of these warnings. Let me clean that up in a second. But let's do the same for loop. Var A equals 0, A is less than 5, A equals A plus 1, print A. 0, 1, 2, 3, 4. It all works. All right, so yeah, let me clean this up. How many are there? I guess it's all disassembly things. Print value, really? It's never used? Well, how do we print then? Let's take a look at our VM. Print. Oh, we just print it here. Okay. So then where does print value get used? GR? It gets used here in constant instruction. Oh, okay. All right. So what are the default features? Cargo, toml. We have debug, trace execution, and debug print code. Pump. Oh, in order to use these, I can't just exclude it for one because then it'll break. Right? It's either both or none. So if either one is present, then we need to compile that feature. Oops. Check. CFG. Oh, it's not in here? It's in our VM? CFG. Yeah. So can I do like config or config? Can I do feature is this or feature is the other? How do I do that? Rust CFG multiple features. I'm just looking for an example. All I'm seeing is the settings here. Yeah, is there a way to use CFG from? Oh yeah, that would work, right? But this is just checking a single thing. Okay. Yeah, like this. Okay, so I can just say feature equals this, comma feature equals the other. So will that do one or the other? Let's find out. Stop. chunk. So in disassemble, copy, paste. There we go. Feature equals what was the other one? TOML. There we go. Debug print code. Let's see if that works. Multiple CFG. Oh. Okay. Rust CFG check multiple features. CFG multiple predicates. This is what I looked at before. Yeah, but how do I put multiple? CFG bang. This is a Rust RFC book. I don't know what that means. Maybe it was here and I just missed it. Right. Oh, there's this thing here. Configuration all, configuration any predicate list. Oh, okay. So I can I do this? Any? CFG feature equals that. No. Can I find attribute any in the scope? Any. Any with a comma separated list. Is there an example? Show me an any. Oh, I see. CFG any like that. Any. Like that. Oh, I have this here. There. Okay. So that's how you do that. CFG any. And I think I need that on disassemble instruction. Simple instruction. Yeah, all these guys. Byte, jump, and constant. So cargo check runs. Let's see if this... Oh, we still have print value. Okay. So there's that. And then the only other one is in chunk, where we have this backwards forwards thing. Okay. That's cleaned up. So this is the for loops, right? Done. Let's commit this change. This is 23.4. Could be happy, could be not happy. Oh, emit jump doesn't need the into. Okay. That was something I just did for emit byte. Yeah. Section 23.4, 4 statements. Okay. Let's take a look at the challenges, since we have time. In addition to if statements, most C family languages have a multi-way switch statement. Add one to CLOCs. The grammar is this. To execute a switch statement, first evaluate the parenthesized switch value expression, then walk the cases. For each case, evaluate its value expression. If the case value is equal to the switch value, execute the statements under the case and then exit the switch statement. Otherwise, try the next case. If no case matches, there is a default case, execute its statements. To keep things simpler, we're omitting fall through and break statements. Each case automatically jumps to the end of the switch statement after its statements are done. Oh, interesting. Interesting. First, we would have to add these three keywords: switch, case, and default. And then we would have to parse them, obviously. For each case, well, we'd have to evaluate the expression, right? And then compare it equal to this guy, right? For each case, we would have to say, duplicate what's on the stack, evaluate this expression, and then compare them. And that would leave a false or a true on the stack. And it would leave this previous expression alone, or the result of this expression alone, because we would have two of them, right? And then we would say jump if false to the next case. Once we hit a true, we would have to pop both of these. We'd have to pop the true off, and we would have to pop the expression off, and then execute the statements. And then at the end of the statements would be a jump forward. So each one of these cases would have to have a patch, right? So we would have to maintain a vector of statements, or vector of case jump patch points. And then at the end, we would have to patch them all to jump to the end. Default is always true, so default would just pop the expression and execute the statement. And then it wouldn't need to jump, because it's going to be the last one. Ooh, I guess it, is that a requirement? Maybe that could be a requirement of making default always the last case. You can't say case, default, and then case. That could be a compilation error saying new case found after default. Because then default would, this would just fall right out into the code after the switch. I don't know that I have the capability to do that right now. I'd have to think about this first and see what would be the best way to do it. Maybe that'll be a good thing for tomorrow's stream, to do switch statements. We did add break statements in JLocks. I remember doing that. Break? Yeah. So we added break statements to JLocks. And that generated a break code. Yeah. And all this did here was, in the parser, it inserted a break node into the AST. And then when we ran it, we saw the break. We had to jump out of the current loop. And we have to maintain a list of all because you can nest everything, right? This time, let's do continue. A continue statement jumps directly to the top of the nearest enclosing loop, skipping the rest of the loop body. Inside a for loop, a continue jumps to the increment clause, if there is one. It's a compile time error to have a continue statement not enclosed in a loop. Make sure to think about scope. What should happen to local variables declared inside the body of the loop, or in blocks nested inside of the loop when the continue is executed? Right, you'd have to pop back to the scope of... That also sounds really complicated. You would have to save the current scope, right? Because you can say while something, and then this starts a new scope, right? But you can also have some code here and then start another scope here, like in an if, for example, if whatever, and then code in here and then say continue. Right, so this continue would have to pop or end the scope for this if statement, but not for the while, because you're still in the scope of the while. But these could be arbitrarily nested, right? You could have another if here. So you'd have to keep track of how far down in the nesting you are from the while that you're continuing from. And then generate the correct number of end scope calls. And then jump back up to the increment, or for a for loop, jump to the increment expression, and for a while loop, jump to the condition expression. That also sounds complicated. I'd need to think about how to do that. Again, so maybe that would be a good thing for tomorrow. Control flow constructs have been mostly unchanged since Algol 68. Language evolution since then has been focused on making code more declarative and high level, so imperative control flow hasn't gotten much attention. For fun, try to invent a useful, novel control flow feature for locks. It can be a refinement of an existing form or something entirely new. In practice, it's hard to come up with something useful enough at this low expressiveness level to outweigh the cost of forcing a user to learn an unfamiliar notation and behavior. But it's a good chance to practice your design skills. Yeah, so Rust, for example, has match, which is a novel control flow feature. And the if-let statements are kind of interesting. I don't know what you'd want to do for locks. Yeah, something to think about. Design note, considering goto harmful. So this is a diatribe on Dijkstra's diatribe? All right, let's take a look at what he has to say. Discovering all of our beautiful structured control flow in locks is actually compiled to raw unstructured jumps is like the moment in Scooby-Doo when the monster rips the mask off their face. It was goto all along. Except in this case, the monster is under the mask. We all know goto is evil, but why? Before I read his thing, I'm going to say the reason Dijkstra, or my understanding of the reason Dijkstra was saying goto is evil, is that it makes it hard to read source code. The fact that we're using gotos under the hood, or jumps under the hood, is not a problem because you're not trying to decipher, or in general, you don't try to decipher the machine code, right? So this would be compiled into machine code instead of this VM code, right? So you're not trying to decipher this unless you're trying to debug some really weird edge case, or maybe there's a compiler bug or something. Whereas instead you're trying to debug this, and this doesn't have any gotos, doesn't have any jumps that you're not already familiar with, right? Everything works as expected, quote unquote, as expected. Whereas this is all bouncy. To try to follow this is complicated, and I think that's Dijkstra's argument, is that all these gotos make it hard to read this, but the fact that you're not reading this, you're reading this, is not an issue. Sorry. The fact that you're reading this and not this makes this part not an issue. That's what I meant to say. All right, so it's true that you can write outrageously unmaintainable code using goto, but I don't think most programmers around today have seen that firsthand. It's been a long time since that style was common. These days, it's a boogeyman we invoke in scary stories around a campfire. The reason we rarely confront that monster in person is because Dijkstra slayed it with his famous letter goto statement considered harmful. Debate around structured programming has been fierce for some time with adherents on both sides, but I think Dijkstra deserves the most credit for effectively ending it. Most new languages today have no unstructured jump statements. C does have goto, but where I use it in my day job is mostly just like the equivalent of throwing an exception. If you're in a large function and you want to just abort, but you have some cleanup work to do, you just say goto fail or something like that, and then in that fail stuff you free up the memory or close to your file descriptors, or you do the cleanup work you need to do before you exit the function. You release holds, unlock mutexes or whatever. Most new languages today have no unstructured jump statements. Yeah, so what do we do in Rust if we need to abort? Is we have the result type. I guess we handle it that way. A 1.5-page letter that almost single-handedly destroyed a language feature must be pretty impressive stuff. If you haven't read it, I encourage you to do so. I'm not going to read it on stream. It's a seminal piece of computer science lore, one of our tribe's ancestral songs. I did read it a long time ago. If you can get past Dijkstra's insufferable, faux-modest, self-aggrandizing writing style. More recently, I've discovered why the use of go-to statement has disastrous effects. At that time, I did not attach too much importance to this discovery. I now submit my considerations for publication because in the very recent discussions, which the subject turned up, I have been urged to do so. Yet another one of my many discoveries I couldn't even bother. Okay. Sometimes you stumble across things and you say, oh yeah, okay, I understand it. I'm moving on. But you don't realize that knowledge could be useful for others. But yeah, maybe Nystrom wasn't too fond of this kind of okay. Anyway, moving on. I read it through a number of times along with a few critiques, responses, and commentaries. I ended up with mixed feelings. At a very high level, I'm with him. His general argument is something like this. As programmers, we write programs, but what we care about is the actual running program, its dynamic behavior. We're better at reasoning about static things than dynamic things. That makes sense. I think that makes sense. He doesn't provide any evidence, but it makes sense that things that aren't moving are easier to think about than things that are changing constantly. Because static things, you have one dimension to worry about. Dynamic, you have two dimensions, right? The thing that you're reasoning about and time. You always have to think of what things are happening when. Thus, the more we can make the dynamic execution of the program reflect its textual structure, the better. Yeah, I don't know. That's a good start. Drawing our attention to the separation between the code we write and the code as it runs inside the machine is an interesting insight. Then he tries to define a correspondence between program text and execution. For someone who spent literally his entire career advocating greater rigor in programming, his definition is pretty hand-waving. Let's now consider how we can characterize the progress of a process. We may think about this question in a very concrete manner. Suppose that a process considered at time of execution succession is a time succession of actions is stopped after an arbitrary action. What data would we have to fix in order that we can redo the process until the very same point? So you have two computers with the same program running the exact same input, totally deterministic. You pause one of them at an arbitrary point in execution. What data would you need to send to the other computer to be able to stop it exactly as far along as the first one was? Right, if only simple statements like assignment, it's easy. You just need to know the point in the last statement you executed. But as soon as you have control flows, function calls, you need something more. Loops make things harder. The unbridled use of the go-to statement has an immediate consequence that becomes terribly hard to find a meaningful set of coordinates in which to describe a process progress. By a counter counting the number of actions performed since the program start. Difficulty is that such a coordinate, although unique, is utterly unhelpful. But that's effectively what loop counter is doing. He's fine with those. Okay. You can define a correspondence for a program using gotos by transforming it to one that doesn't, and then using the correspondence for that program, which according to him is acceptable because it only uses branches and loops. We're both using pretend math and fake logic. Okay. So what's the comparison here? Oh, I see. So you're saying, yeah, if in order to break out of this, you have to break. Locks and other languages have the ability to use a break and specify which for loop you're breaking out of to make things easier. Here, this is go to done. Just breaks out of all of the for loops directly. I think my issue with GoTo is it makes it hard to figure out what the control flow is if you're using it for spaghetti code like early basic programming, where everything is GoTo everywhere. That's the hard part. If you're using it this way, this is fine. But like I said, Rust and other languages also have a way to break out of a specific for loop. You just put the tag on each one of these and you can just say which one you want to break out of. I guess what I really don't like is that we're making language design and engineering decisions based on fear. Few people today have any subtle understanding of the problems and benefits of GoTo. Instead, we just think it's considered harmful. Personally, I've never found Dogma a good starting place for quality creative work. All right, so I think we're done with for loops. Right, we're done with all the GoTo stuff. Maybe we can dive right into calls and functions and see how far we can get in the next half hour or so. This chapter is a beast. Oh boy. Guess we're not finishing this one today. I try to break features into bite-sized pieces, but sometimes you gotta swallow the whole meal. Our next task is functions. We could start with only function declarations, but that's not very useful when you can't call them. We could do calls, but there's nothing to call. And all of the runtime support needed in the VM to support both of those isn't very rewarding if it isn't hooked up to anything you can see. Oops. So we're going to do it all. It's a lot, but we'll feel good when we're done. Eating consumption is a weird metaphor for a creative act, but most of the biological processes that produce output are a little less decorous. Okay. Thank you for that. All right, function objects. The most interesting structural change in the VM is around the stack. We already have a stack for local variables and temporaries, so we're partway there, but we have no notion of a call stack. Before we can make much progress, we'll have to fix that, but first let's write some code. I always feel better once I start moving. We can't do much without having some kind of representation for functions, so we'll start there. From the VM's perspective, what is a function? A function has a body that can be executed, so that means some bytecode. We could compile the entire program and all of its function declarations into one big monolithic chunk. Each function would have a pointer to the first instruction of its code inside the chunk. This is roughly how compilation to native code works, where you end up with one solid blob of machine code. But for our bytecode VM, we can do something a little higher level. I think a cleaner model is to give each function its own chunk. We'll want some other metadata too, so let's go ahead and stuff it all in a struct now. And I'm starting to feel where this is going, and I'm not liking it. I'm going to take a quick look at my VM here. Oops. Oh, wrong directory. There we go. So what I have right now is we create a VM, which creates a chunk this way, and then we interpret the source by compiling it first. If we're going to have a separate, and then what I do is I say, okay, we've compiled this chunk into here. How is the compiler going to compile multiple chunks? And this is saying, okay, well, each function is going to have its own chunk. And now my issue is how do I run this? Because right now the chunk is just a quote global inside our VM. So if we're going to call a function, we're going to have to be able to replace this chunk with the chunk we want to run. And then when we're done with the function, we have to undo what we just did. Which, okay. Let's see how far we can get. I removed object. We don't have object anymore because what I did was I put everything in value. We originally had the string object. Here it is, object string. And so I just shoved it in here because I was struggling trying to make a nice representation. If I say object, then we do need an object something. Oh, sorry, function. All right, that's what we're doing, is we're creating a function. Functions are first class in lock, so they need to be actual locks objects. Thus, object function is the same object header. Then we have the arity, which we remember from last time, how many arguments it takes. We have the chunk, which is the code of the function. Okay, I should just read this. The arity field stores a number of parameters. Then in addition to the chunk, we store the function's name as an obj string. This will be handy for reporting readable runtime errors. Humans don't seem to find numeric bytecode offsets particularly illuminating in crash dumps. All right. So what do we do? Right, because we need the arity and the chunk and the name. I could just create pub struct function, which has arity, a chunk, and the name. And this is going to give us warnings. Oh no, errors not found in the scope. Okay, so we're going to have to add use create chunk. Equal can't be applied to chunk. Does that mean we have to write our own? The only reason we need partial equal and partial OR is for these first three, I guess first four for equality. So this is going to be annoying to have to do, because we're going to have more than just functions, right? We're going to have classes and objects as well at some point. Self? It's just like this, bool. Oh, self and other. I can't remember if it's with ampersand or not. And then I guess, how do you compare them? I'll just say false for now. They're not equal to each other. So now partial ORed. And I can't remember how to write that. So let's just copy this. And it's check self, right? Oh, right. And then in order to clone, how do we clone a function? Value func f is going to be value func of function f dot chunk is chunk f dot chunk dot clone, I guess, and then name is going to be f dot name dot clone. Right? Oops, I forgot the closing brace there. Oh, we can't clone a chunk? Oh dear. Yeah, so how do we clone functions? And is that something we even want to do? And then value array needs to be copied. Oh, that's interesting. So yeah, that's right. The value of okay, so that part's done. And then for display, how do we print that out? Is it going to talk about it here? This stuff we can do. Okay, in object, yeah, we can create a new for it. How do we print it out though? Maybe this should be in its own file. Let's create a new file. And just move these guys over. And then import it here. And then, of course, in main. Otherwise it won't work. And then in value, I guess. Oh no, in function we need to, oops, this doesn't belong here. This belongs in value. Here, format, let's just say value function f. It's going to be right, bang, f, f. Very simple. And then we have to implement display. Oh, we still don't have this. Use crate, chunk, star. All right. Oh, and this is a private field. Function. We want to say function.clone. And then I could just write a clone for it. Huh. Okay. Impl clone for function. I'm confused. The reason I'm confused is because why did f.clone work? Right? Fn clone. I'm just going to do it. Self to do. Okay, so now that stopped complaining, and then I have to write display for it, right? Let's take these two lines, put them here, and this, instead of this, it's for function, and this is also going to be a to-do. Right. Okay, we still have a problem. Method not found in function. Oh, because I'm using f. That was dumb. Oh. There. Okay. But I have no idea if this is actually going to be any help at all, because now we're all squirrely here. How do we? I know how to clone. Right, function arity is going to be self arity. Chunk is going to be self chunk clone, and then name is going to be self name clone. So that's that. How do we do equality and partial compare? We should never do this. Panic. Comparing the ord of two functions. What do we want to do for equality? Can't just compare the name because, oh, yeah, because you could have multiple. I'll just say they're all not equal to each other. Okay, and then we'll see what breaks after that. And then display we have to figure out. So this is the new, which we don't have yet. Impl function pub fun new function. I guess we need to be able to pass in. This is just allocate object, and it doesn't set anything here. So arity is going to be 0. The chunk is going to have to be replaceable. That's annoying. Standard cell, F cell. Chunk is going to be ref cell of new chunk new, and then the name is going to be blank. Right? Okay, and then somewhere we have to create a new function. When we're done with that function object, we must return the bits of bar back to the operating system. Yeah, so this is freeing the chunk. We don't have to worry about that in in Rust. Locks lets you print any object, so print as function. Okay, so this is the way we do display here. So let's just follow that. Print, bang, because there's no new line. Fn, this, and it's just self-name. Like that. Epic Blog says, wait, you're back to putting the chunks into ref cells. Wasn't RC sufficient? This is, yeah, now I'm doing it in terms of the value array. The reason I just did ref cells because if we're creating a new function, we need to be able to replace. We need to be able to blindly do a replacement with a new chunk when we create the chunk. Yeah. So when I did RC, that was in the VM, right here, and I've got a feeling I'm gonna have to modify that to be a ref cell as well, based on what's coming up next. I don't know what's coming up next. This is going to be a little tougher, I think, than I was anticipating for today. Right now, our compiler assumes it's always compiling to one single chunk. Yeah, and the VM assumes the same thing. We compile to a single chunk. With each function's code living in separate chunks, that gets a little more complex. When the compiler reaches a function declaration, it needs to emit code into the function's chunk when compiling its body. At the end of the function body, the compiler needs to return to the previous chunk it was working with. That's fine for code inside function bodies, but what about code that isn't? The top level of a LOX program is also imperative code, and we need a chunk to compile that into. We can simplify the compiler in VM by placing that top-level code inside an automatically defined function too. That way the compiler is always within some kind of function body, and the VM always runs code by invoking a function. It's as if the entire program is wrapped inside an implicit main function. One semantic corner where that analogy breaks down is global variables. They have special scoping rules different from local variables, so that in that way the top level of a script isn't like a function body, right? Before we get to user-defined function then, let's do the reorganization to support that implicit top-level function. It starts with the compiler struct. Instead of pointing directly to a chunk that the compiler writes to, instead it has a reference to the function object being built. We also have a little function type enum. This lets the compiler tell when it's compiling top-level code versus body of a function. So if we look at our compiler, the compiler currently maintains a chunk. But what this looks like it's saying is this should be a function instead. Right, here's the locals, for example. And then we have a function type, which is either going to be a script or a function. So then what happens as we go through different every place the compiler was writing to the chunk now needs to go through that function pointer. Fortunately, many chapters ago, we encapsulated access to chunk with the current chunk function. We only need to fix that, and the rest of the compiler is happy. Yeah, except I didn't. So, oops. Every place we do self chunk, right, which is everywhere, we want to point to the current function instead of the current chunk. This is everywhere. Okay, so if I change this, I'm just going to comment this out here, and I'm going to add. Why do I have to use create star like this? Function star. I wonder what that's going to bring. Okay, let's see if this still builds. It does not. Oh, interpret result. Is that in main? It is. Okay. I probably should put that in its own little file. There. And then save that, and then wherever we need it, we'll just import it. It's not in chunk, it's compiler, right? And VM needs it also. Why did I do it this way, this here? And okay, I should be consistent. I don't need superstar anymore once I do that, right? And then main needs it. Mod error, use error, star. And then print, it doesn't like print. Oh, this should be right. Okay. All right, that's a little cleaner. Let's go back to compiler. And what I was going to do was comment this out. And okay, but before I do this, let's no. We'll say function. And then it has to have the function type. That's a little frustrating. And if I do that, then I no longer need the tick A anymore. I don't need a lifetime. Why did I originally have that lifetime in there? I don't remember now. Oh, because we're writing into... Yeah, it saves it here. It saves the chunk directly in... So we still need the chunk. Now I'm wondering, okay, so what am I doing here in the VM? Right? Because in the VM we create a new chunk and we pass it in and say, okay, fill this chunk in with the code, and then or use this as the chunk for the code. Oops. And then I tell the compiler, compile to that chunk. But now we're going to have a separate function. Oh, we're going to have a separate compiler for each. How's this going to work? Oh boy. So all this is doing here is actually just, this is refactoring this so that we can actually get where we need to go. This is in creating functions at compile time. What we're doing is actually creating the function for that has the chunk. So in compiler, we init compiler and say that we have a script. This is our new compilation. If we take a look at the code, fn compile, right? This is where we call the scanner. Here we're generating a new compiler instead. So this still has to happen. It's just that Okay. Creating an object function in the compiler might seem a little strange. Function object is a runtime representation of a function. Right, so we had this chunk, and now we have this thing here, and the VM is the thing is creating it, but it shouldn't be. Right, we should be just passing the source. Yeah, we are passing the source into compiler. But what we need to do is ask the compiler, after compiling the source, ask it for the script function, I guess. All right, this is saying current is equal to compiler, and then we set the locals up. Existential misery. Thank you for the follow. I wish that I was actually having some more interesting code writing right now. To thank you for that. But right now I'm just stuck on the right way to organize this. In the VM, we want to create a new compiler, just like this, except we don't want to pass in this chunk that we created here. What we want to do is just pass in the source to compile and let the compiler compile the source for us and return back the chunk that needs to be executed, right? I'm just trying to scan forward to see, do we have anything in the VM that needs to change? No. The VM, the VM, let's go back to where the VM was created. Let's go over here because this has a better view. So there's scanning and here's compiling. And we're gonna, let's see. Right, so the compiler hooks the scanner to the VM. And this is what our interpret code looks like right now. And if I take a look at it really quickly, let's do this. This is what interpret looks like, and this is what the original interpret looks like. We created this chunk, we initialized the chunk, we compiled the source into a chunk, and that's what I was trying to do here, where we created a new compiler and passed in the chunk. We passed in a mutable address to the a reference to the chunk, sorry, and then we say compile the source into the chunk. We grab the chunk in the VM and then we execute it. Right, we just call run, and run runs whatever's in the chunk. So this is the way I implemented that. Here's the run. We don't have to free and we don't have to return a result because run returns the result for us. Existential Misery says, hey, I'm very new to Rust. So am I, actually. I still feel like a total beginner. So welcome. So how do we want to do this, right? We want to what this is doing here. Embrace that feeling, Epic says. No matter how much you work with Rust, you'll always feel like you're new to it. Yeah, at some point I want to feel a little more fluent, though. Just a little. So what's happening, so we've created the function object. We know how to create new functions, and I've done all of that. What we're doing is compiling to function objects, right? That's what we're trying to change, is how the VM still is calling into the compiler and saying compile. But this current, so this compiler says compile the compilation into source. what are we doing with this chunk here? Are we just going to shove it into... Oh, does that make sense? Is when we do the init compiler... Let's take a look again over here. Oh, we've already done the init compiler, right? When we get to this interpret part. Where's init compiler? Let's see if I can find it. So that's not in this chapter. It must be in... Yeah, it's got to be, right? This is the compiler. Unless init compiler's a new function? Yeah. We're still going through the compile, which is the main entry point, which is here. Right, and now instead of we're calling init compiler, we're passing in the compiler, and that's going to set up the new function. And it's resetting the locals. Okay. That's interesting. So local is equal to this, and it sets this up, and then it drops it on the floor. Oh, it just grabs a new local and inserts it into the locals. Okay. Compiler implicitly claims stack slot 0 for the VM's own internal use. We give it an empty name so a user can't write identifiers that refers to it. I'll explain what this is about when it becomes useful. Right, so we're just pushing, we're doing a quick push of an empty locals. But that means we'll have to be able to write to it. Or Epic says learning is fun. I agree that learning is fun, but struggling trying to express yourself is not as much fun. So what I need to do is get this function's chunk, and write to that. And I think, see, that's going to change as we... Right, that's going to change as we go along. Which is why I'm doing that now. So the chunk itself is going to have where's fn new? Here. At the bottom of this, we're going to put the function, a new function. So function is going to be refcell new function new. And the chunk is going to be part of that. Oh, let func is equal to ref cell new function. How do I create a new function?
I don't know what y'all think, but I think that's...
Of course I don't have it. I don't have to pass in anything. Oh, I can pass in a new with chunk. And is that what we do here? We just call new function for the compiler. Epic Blog says, tip, if you're unsure what the final type will be and you suspect it may change, you can create a type alias. You still need to update the code, but you only need to update it, the code in one place, the type in one place. Tinfoil What says, have you tried tree sitter for the highlight? I'm not sure what you mean by that. So I don't know what the type is going to be, and I'm just doing ref cells or whatever. What you're suggesting is saying create the type up here. like that, and then just using that here. What? Yeah. And then function here. So refcell new function new with chunk. And we're going to use the chunk that got passed in. Oops. Like that. I don't want to clone it though, because that's where I was going with this, right? We'd say function or self. Arity 0. When we say new function, we give it nothing, right? But we need the chunk. We need a writable chunk. And that's why we have this ref cell. So maybe I can just say set chunk, pub set chunk, and pass in. Perkin says, and how do you edit the function, or do you just stick with ref cell? That's a good. Well, I mean, the function itself has. Yeah. Okay, that's a good point. Perk says, how many times are you going to be able to call this function from a higher scope? I don't know. I don't know. What I need to do actually is just sit down and think about what approach I want to take, because I didn't, I try to avoid spoilers, so I didn't read this ahead of time. So I think now that I'm reading through it, I think I need to reorganize. Let's quit out of all of this. Not do any of that. Git status. Oh, git diff. Do I have any? Does this compile? Cargo build? It does, just with a few warnings. Okay, so we got to a point where it compiles. Tinfoil Watt says NeoVim has tree sitter support now. It's a really good tool experience. I'm not familiar with tree sitter. I can take a look at it, I suppose, after the stream. All right, so what I'm going to do, here's the plan of attack. I said that I wanted to do these the first two challenges tomorrow, but that was before I realized how difficult, the difficult thing I was getting into with compiling function objects. So I need to think about the right approach to how to handle function objects. Because obviously we need to be able to create the function running inside that has the chunk inside it. And the way I organize the code is different to the way he's got it. And he just references the chunk that way. Whereas I've got the chunk everywhere inside the compiler. If I look for self chunk, right? It's there, it's there, it's there, it's there, it's there. So every place we have to say self function. This is what I want to end up doing, right? Self function chunk, and then be able to replace the function after a time with another function, right? Because the compiler is going to have to get called. I'm going to have to look to see, does it get called per chunk, or is it called per source? And the source just generates a bunch of chunks, and we're going to have to do function replace. Let me just scan forward here. Call frames, allocating local variables. Right, so each one of these is going to have to be its own function. And now we're talking about call stacks and call frames. Yeah, and that's in the VM though. So the VM can handle it on its own. But how does the compiler? Wow, I'm getting really annoying and obnoxious with all this scrolling, aren't I? So the compiler returns a function now instead of returning a chunk. All right, if I take a look at VM, what we compile. Oh, what it was returning was just a result before, and now it's returning a function. So maybe that's what we need to do. And that function is going to be the top level script. Yeah, there's init scanner. And then object function end compiler, and it returns the function. All right, so that's where we're going with this first part. We're returning the function to execute, and then the VM, instead of getting a chunk to execute, it's going to have a function to execute. Eventually, we'll update interpret to handle the new declaration of compile, but first we have some other changes to make. Okay, so I think I see where this is going now, right? So compiler does the compile, and then this is going to say, instead of passing the chunk, why are we doing it here? Why don't we just have it pass back? You can say let function is equal to compiler compile source. And then instead of saying self chunk, we say self, and we can say self run function. And I remember trying to do something along these lines before and running into lifetime problems. But if we're passed back the whole function, right, and then this would take a function, and then all of these self chunks would change into functions. And that's a problem, of course, because in runtime error, we need to be able to get the current chunk. So it might, it might be that we have to say self chunk is equal to function chunk, right? Or replace, self chunk replace with function chunk. And then at the end of the loop, we put it back, right? Because maybe we're going to end up doing multiple runs, right? Every time you encounter a function, maybe there's opcode call or something like that, then we'll grab the function call. I'm just guessing here. Is what we'll end up doing is saying self run self local function pop function or something like that, right? And it would just pass the new function in, and then that would get shoved onto the chunk. And then after we're done with the loop, we'd say, oops, self chunk replace previous. And that would put the old chunk back to execute in the VM. That's along the lines I'm thinking right now, but I obviously have to play around with it. Git status, git add source, git commit, starting work on functions. All right, let's get that up to GitHub, and I will play with that tomorrow. All right, thanks everyone for hanging out with me. Yet another one of my infamous cliffhanger streams. And then hopefully tomorrow we can, I'll have some better ideas about how to implement all this and get the VM working properly with handling functions instead of chunks. All right. Have a great rest of your day. Take care.